next talk will be held by Maggie and Mickey. And yeah, on that point, I think we can all agree that documentation is an essential part of creating and developing on a platform, like on an Intel platform, for example. That's like some platform, for example, Intel. And most of these documentations tend to be like on a lookup basis, so they don't really have a step-by-step guide on, oh, I would want to do this, so how do I get there? Well, these folks here have a pretty nice talk prepared to do exactly that. So please give a round of applause for Maggie and Mickey.
Hi, well, my name is Maggie Howdigi. I work for Intel, and this is
Mickey, and I don't work for Intel.
So it'll be an interesting talk. You have kind of 2 points of view. One, Intel proper, these are features and these are this is how things work. And then you get an external point of view of
how to actually use this in real life.
So firstly, a little bit about what this talk is not. This talk is not going to teach you how to debug. We assume this is a conference full of firmware experts, so we're not going to teach you how to do that. We're also not going to teach you how to use a UI. We figure you are competent enough to do that on your own. We will talk about features and a suite of tools that are available and different ways to do breakpoints and the way to run chipsec within DCI. Yeah, let's dive into it. Closed chassis debugging. So this is exciting because it changes the way we've done it for years and years. So you no longer need open chassis, $3,000 proprietary hardware to do this. You can now do this pretty much for free or with a $10 USB cable. Right. It has UEFI platform firmware support in every stage of boot. And yeah, it's pretty flexible.
Yeah.
So let's talk about DCI. There are 2 ways you can do it. DCI is supported from Gen 6 platforms and beyond. If you wanted to use it on previous platforms as a host, you can use something called the CCA, a closed chassis adapter that implements DCI for the host, and it'll work as well. The CCA is available through Intel, and it costs about $400. So we went from needing to open the platform and needing a $3,000 part to do it to $400 to A to A USB cable that just clips VCC, which is available through Intel for $10, or you can DIY it.
So just a quick note, the CCA box does require you to sign an NDA with Intel. However, if you go to DataPro, which is a cable supplier from Seattle, you can buy the USB A to A cables, make your own, or buy the Intel cables from Mouser, which we recently discovered happily. You can get the USB A to A or A to C. So A to C is $50 and A to A is $18. These are the yellow cables. The non-Intel branded cables are orange and black, and they go for about $10, $15 for 3 feet. And it goes up from there depending on the length of the cable.
So 6th gen and above, these are the limitations. You need additional hardware, so you'll need the debug adapter and/or cable. Manufacturers may disable their specific settings that you need to go and set up and enable them. These might be removed, which Mickey has some experience with as well.
Well, basically, there's 2 main things that you need to have enabled to do proper DCI. One is the IA32 debug MSR. You need to have it flipped on for the CPU to be halted. And the other is to enable DCI, the HDCI EN. That's the register. If you want to look it up, it's in the Series 100 chipset datasheet. After that, it disappeared. So if you need a reference that's where you can find it.
So I'm also part of the team at Intel that supports ChipSec. So we're part of the larger organization that delivers our UEFI solutions, platform code, and as well as Tiano, part of the team that, for example, Vincent Zimmer is a part of. We also are the team within Intel that supports ChipSec, and we also help Intel Bug Bounty for UEFI stuff. There is a ChipSec module that you can just test to see if DCI is enabled. It checks for a couple different things. You check the E-control register to see if a DCI is enabled on the PCH. It also checks MSR I32 debug interface to check whether debug is enabled, to check whether debug is locked, and whether debug has occurred. That might be interesting if you notice that debug has occurred on your system and you potentially haven't done it yourself. So you'll get warnings and/or failures accordingly.
Anyone here is not familiar with ChipSec? Okay, we got a few.
Awesome.
Few plus one. So
yeah, let's touch on that.
You want to do an overview?
Sure.
Your team?
It is my team, but it was initiated by
my boss.
Your founding fathers.
I work for a startup that our CEO was the creator of ChipSec. Basically, it is a tool allowing you to do security verification, validation, and exploration of your platform. Think of a nicely written, comfortable Python framework to play with a CPI, MMIOs, all the UEFI stuff that you can think of, the SPI, and more, and so much more. So if you want to deep dive into your Intel-based platform, you can use ChipSec as a tool to get there and see how things work under the hood.
So the configuration of a platform is pretty complex. There's a ton of registers and a ton of logs and a ton of things. And the more vulnerabilities are discovered, the more stuff there is to check. And it's different platform to platform. So one of the brilliant things that I think Yuri did back when he used to work at Intel is if one person knows a brilliant thing and goes and checks for that, and good for that person, but he created a framework that is now kind of the standard that everybody tests against. And it's open source, and we find it to be very valuable. Like I said, we also work with the Intel Bug Bounty, where every time we get the exploits developed by researchers around the world, so we can tool it back into ChipSec and make sure that the bar is raised and everybody can test to the same bar. It's not just a scanner, though. A lot of people just think of ChipSec as, okay, I passed or I failed. It also has a bunch of tools and util commands to go read and write to different things. You can read your PCRs for TPM. There's fuzzers, so you can do a whole bunch of interesting functionality. And the fact that as of version 1.36, you can, when you're doing debug over USB on your platform, you can run ChipSec at different parts of the boot. So you don't get just a runtime scan of what your registers look like. You can see like a 3D view from the moment I boot to all the interesting points, what my registers look like, or try to do some potentially destructive tests, see if it sticks through the boot. So yeah, that was recently added in November of last year.
Yeah.
Yeah. All right. So other limitations. In order to be able to do debug and load the symbols, so you can do source code debug, you need to flash a debug image and build it yourself. And we'll go through how you do that. Intel System Studio supports Linux, Windows, and Mac OS. And its debug is not optimized for performance. Obviously, some of our demos that we'll show a little later are kind of sped up because it takes
a while. You don't want to take the JTAG and go over and then do all the magic to translate and go back. It's
millions of lines of code and all the debug messages there, so you can imagine.
Yeah, there's that.
It's not built for speed.
Yeah.
So Intel didn't just enable the platforms to be able to do to enable the JTAG interface. We also provide a suite of tools so that you can do this. This is freely available online with a free 90-day renewable community license. You can go request it. It usually takes a few hours to maybe a day. So you get the license and you can just renew forever.
Well, you basically you go through the usual EULA and whatnot. You get your software, you're dandy for 90 days, and then after about 80 or 75 days, you get an email saying your license is about to expire, and click this link to renew, and you're golden. So if you want to, there's a lot of tools in Intel System Studio. So if you want to explore it and use it, it's up to you. But if I get a chance, I think we can show pictures of how the debugger works specifically.
Yes.
But
We have some
we'll-
screenshots, and then the backup has way more step-by-step
Yeah.
stuff. All right, so basically you launch the IDE, you click on the debugger button there, and the debugger is enabled for Intel Atom, Intel Core, and Xeon platforms. You can debug UEFI firmware. It's OS aware and is able to do kernel module debug. You get full CPU register description and BitLoader editor, which can be useful. You get access to page translator and descriptor tables, etc.
And more and more and more and more. So if you want to have a secondary platform, you want to develop like a kernel module or a Windows driver, and you want something that gives you visibility without, I don't know, stuttering once in a while. Using the Intel debug hardware is pretty cool to see it happen. For example, when we gave a talk 2 years ago at DEF CON, we found a buffer overflow in BIOS. And to debug the exploit, we use DCI, which is amazing. So imagine you have to look at memory and look at code executing when your bug triggers in BIOS, and you just watch the NOP sled and you step through it. It's quite interesting to see, and it's very simple to use. So that same principle applies to anything you'd like to do. So if you'd like to look at the kernel, a specific module, or anything during boot, you want to pause, you can set up a breakpoint. And it's not limited just for debug. Debug gives you symbols, but you can also do this on release. And you can halt the system at your convenience and set breakpoints for reset vector and whatnot, SMM enter, and so many others. We'll talk about this.
And hopefully it's a feature that gives more platform transparency, that enables service to happen in a much more accessible way. You don't have to send it back to the manufacturer. So, all right, let's see how we can debug for UEFI. So what you're going to need is Intel System Debugger, Visual Studio, the EDK environment for building the Aeon Up-Squared. So we chose to work on the Up-Squared for this presentation since it's a poor CCI, like Minnow doesn't.
Somewhat open sourced, and it supports DCI.
All right, so this is our Celeron NC3350.
Yeah, these are
processor,
$200 on Amazon Prime if you're US-based.
Apollo Lake, Broxton platform. So in order for you to build the platform, there are, you can go get the code base, and the release notes include the step-by-step process for you to go build it yourself.
It's pretty straightforward. I use Windows, unfortunately, for most of my work. And no offense, Jeremiah. But it takes a while, right? So it's a simple step-through guide, but to build BIOS, I don't know why. It always takes like at least an hour to get to the point where you can build it. So you have to install Visual Studio the proper way. And Python, if you have multiple Visual Studios, you have to make sure that you don't mix everything together. So my advice to you is, if you can run this all in a VM, do it. It might be a little bit slower, but at least you get a clean build environment that you can trust.
And repeat with.
And repeat it, yeah. Because at some point you want to install Visual Studio 2019 and it messes up a path somewhere, and then you just, yeah. stuff.
The step-by-step instructions are there, and let us know if you have problems.
Yep.
So debug is obviously slower put, larger image, it's clunkier, but you can use the serial port to get all the debug output and see things like a certain trace errors.
Oh yeah, there's a lot of stuff coming out of serial if you boot and debug. And it takes, what, like 8 times slower than release? But yeah, but you get a lot more insight into the code.
All right, so let's see how we could step through the BIOS code. So we need to be in protected mode in order to do this. So we can break on reset and then step over, step from the reset vector to jump into protected mode. Once we're in protected mode, we can load the symbols if they're not already loaded with the load this tab. And it'll, again, work on all the faces for UEFI, SecPI, Dixie. And you can set which modules you're interested in, and it'll halt on entry for each one of these modules. So in order for you to start an agent-based debug session for UEFI, you select UEFI agent in the connection method, click connect, power on your target, and then you can add the names of the UEFI modules that you're interested in to the watch list. And the debug target will halt every time a module matching the name to the watch list is loaded. And you'll need to delete those breakpoints so you can see the subsequent ones. But this is pretty useful. So you can stop in PI, you can stop in Dixie, you can stop wherever you want, and we'll teach you how to set different types of breakpoints as well. Breakpoints. So there's a few different types of breakpoints that you can do. There's a drop-down menu that you can select specific things like break on reset or break on SMM enter. We have an example using that at the end, a little video of a script Mickey created. Some of you may be familiar with CPU dead loop, which is basically what we used to do. We'll set an infinite loop there so that it'll stop basically, and we can debug starting from there. The problem with doing that is that your system trace is probably going to be filled with stuff that's not very valuable or interesting to the specific thing that you're trying to do. So there is a better way, a special DCI breakpoint, something called an ICE breakpoint. It's an Intel architecture opcode called int1. So it'll halt the processor, and you'll have the correct trace information that you expect, and then you can just step over it. There's no C equivalent. It's assembly code, and it's just basically this tiny little blurb of int1 and then just ret. You add it to a file called CPU breakpoint.nasm. You include it in your /i32 and /x64 directories, and then you just call them from the C file. CPU breakpoint, you define it as an external void, and then you just call it and make sure to include the NASM files in the INF file. Build and repeat. Oh, you also need to make sure to enable the exception handler in the console so that you can trap it. So basically, you choose the thread that you want to break on, and then you do thread, whatever thread ID you want to break on, breakpoints, add int1 exception. And now for chipsec fun. All right, so we walked a little bit over about what chipsec is and all the forensic capabilities that it has. You can see what drivers are loaded, which ones are blacklisted, whitelisted, etc. Look at the TPM, do a whole bunch of stuff and tools. As of release 136 of late last year, we have DAL support, and that enables us to break somewhere and use chipsec on the Python console.
which we'll show in the demo at the end.
The formatting for chipsec is a little different. So basically what you want to do is just install System Studio, then install Pi132 and set up tools. These are, so you clone your chipsec, you install chipsec, connect and halt the platform, and then you import chipsec. So for example, import chipsec_main, and then you can run chipsec_main.main. And if you want to run a specific module, there's a bit of funky parentheses and a comma syntax here, but you can run just the BIOS write protect, or you can do logs. The logs will be saved to the place where your Python console is running from. So it's typically C Intel DAO, but
could be anywhere, program files, wherever you installed it.
It's from wherever you're running it from.
Or in Windows.
Okay. Do we want to do that now?
Can you see that? Oh, no. Okay. Can you see the text in the back? Or I need to be a little bit bigger. Is it better? So don't want it to get cut in the corner. Windows keeps snapping it back to. That's the biggest I can get it. All right. If you can't see it and you want to see it, just come closer. Basically, this is the Python console starting up, the DAO, connecting to a Skylake laptop that I have with me. It's Dell Latitude. So just a quick disclaimer. There's a timer at the bottom. It shows real life time. It's sped up, so you'd understand, you get a grasp of how long it usually takes. So to start up, set up, and halt, it takes 45 seconds, give or take, from start to finish. Now that we have a console, we import chipsec. In this case, chipsec util. I call SPI read. I want to read 20 hex bytes from position 0 from the SPI. It halts the CPU, and it reads the SPI content. There you go. This is the beginning of SPI. And ITP go lets the CPU resume. This is kind of awesome if you tend to deal with a SPI often, but a caveat is this is very, very, very slow. If you want to dump the whole SPI using ITP, you better go for lunch.
Probably an hour.
Yeah, about an hour, 8 megs. But if you want to do specific stuff, anything chipset can do, you can do with ITP. At any point, you halt the system.
Which is at any point during boot, which is pretty powerful.
Yeah, so from the reset vector onwards, then it's up to you.
We chose to do this demo because it shows a little bit of the functionality and a little bit of what you can do. We thought showing the different breakpoints of the different places would be kind of anticlimactic of like, oh, look, it stopped. And if we step over, it stops again. But if you have thoughts of things you want to do or a platform you want to try to get going, come find us later and we'll help you do it. We can do a sample app and just put a breakpoint wherever. And yeah.
Yeah, if you want to see, if you want to ask more specific questions or more, personal issues that you want to discuss about how to do this on your own computer or whatnot, feel free to catch us afterwards. I have the cables with me. If you have your computer with you, and you want to live dangerously, we can do it today. And
the point of the talk really is we have these features. We have the software go forth and debug. We can do this on closed chassis. We can do these on production systems. You can do it over USB, and you can do chipsec over it. So go ahead, give it a shot. Let us know if you have questions. For any chipsec stuff, there's always chipsec@intel.com that goes to me and my team. Yeah.
There's
another video?
Yeah.
Oh,
again, once you
this is kind of the end. So you want to do that before I say thank you?
No, I'll say thank you and then
say thank you.
Yeah.
Lori, thank you so much. They have a ton of material, including the stuff we've presented, but so much more. There's training and stuff. Go check out Tiana Core on GitHub. And of course the chipsec team for enabling the hardware abstraction layer to be able to support DAO. I think that's pretty powerful and pretty awesome. So I think it's definitely a good thing for our community.
And one more?
Oh, because lawyers.
Yes. There's also the backup. You want to just flip through it?
There's a bunch of stuff in here.
Yeah.
You can go look at it.
Yeah,
It tells you where to get stuff, where stuff is, all the different things that are available.
Like what's what, where's where.
Yeah, where the trace is, where the breakpoints would be.
It's good for reference.
Connect, disconnect.
You don't know the ID.
This is your console window. You click to connect, you select the probe, which is usually DCI, what platform you have, yada yada.
Right.
You can resume, halt, restart, step over, step into. You can look at your threads. You can see all the register flags. You can see variables, page tables.
That's it.
All the things.
And that's the Intel side.
And now it's Mickey's side.
So one more demo that is kind of interesting is so this is not new. It's on the internet for almost 2 years now. If you're interested in SMRAM and stopping and looking in it and playing with SMRAM, there's like a 10-line worth of script that allows you to dump SMRAM. So this is an example of how to do this from ITP in a script. It's principally very simple. You tell ITP to breakpoint on SMM enter. You issue an IO on B2. You halt the CPU in the process. You continue. You wait for the breakpoint when it gets the SMI. You break on the SMI. You're executing in SMRAM, and you just dump it.
And this isn't one of the breakpoints that you have to go code and build. It's by default part of Intel System Studio drop-down break on SMM enter. It's built in. Yeah,
it's among the other things, there's VM enter, VM exit, SM enter, SM exit, reset vector in it. There's all kinds of cool stuff there. A little bit of time until everything starts up and connects and everything. But once you connect, you can start playing with it. One caveat I forgot to mention, you might get your platform into an inconsistent state. So if you do end up playing with registers and don't complain if you do brain surgery on yourself. So don't blame ITP. Blame the platform you're messing with. It goes, we halt the CPU. We set the breakpoint for SMM enter. We issue the SMI. We break an SMM. And then we just dump the SMRAM. Now, this takes a while, so I'll sped it up a little bit. But as you can see, I take the contents of SMRAM, and I write it to ctemp, and that's it. Pretty simple. Now, the target you're going to use it on, it's either a development board. So like Up Squared, you buy this. You buy this platform on Amazon. It's like $220 or something like that. It doesn't come with a power supply, so you need to buy the power supply. And you download the debug image from Intel. You flash it. You can flash it just through USB, which you don't need a flash programmer, or use a flash programmer. And then you just go on and have fun. But if you have a laptop that is Skylake and over, like 6th gen and above, that is, or not just a laptop, a computer platform, anything that's Intel-based, 6th gen and above, that you want to play with for your own amusement or work or whatever, I recommend MSI, Gigabyte, all the good manufacturers that leave a lot of things unlocked. So you get one of those boards, you put in a CPU in, and then you go in the process of basically enabling DCI and enabling CPU debug. I did this to a laptop. If you want to get an example, I bought a used Dell Latitude 3470 for $100 off eBay. It's a 6100 Skylake machine. I have it with me if you guys want to come play with it later. What I did was I didn't even open the chassis, booted into UEFI shell from a USB stick with chipsec, dumped the SPI, found the setup variable, used the iFire extract to look at the settings, found the right settings for DCI and CPU debug, enabled them through, again, booting through a USB device using a tool called ru.efi. If you're not familiar with it, it's a cool EFI tool to look at the variables and look at all kinds of information on the platform. I wanted to show it to you, but the projectors didn't really like UEFI video, which makes sense. I was just hoping to. But anyway, I'm just going to go through the process of doing this off-platform so you can get a sense of how it works.
So normally you would just go to setup when the system is booting and just go to the DCI settings and toggle them on. If the settings are removed, then you can play with the HII database and go find where they are and toggle them back on so you can modify them. And that's what Mickey's doing here.
I already have the GUID for that setup variable. So basically, I open the dump that I got from the SPI in UEFI tool. I look for that GUID, which is setup, right? I extract the P32 body, and I'm done. Next step is use the RF extractor to get the values off it. Basically, both of these tools are by Nikolai Schley. You can find them on GitHub. They're open source UEFI tool, and the IRF or IFR extractor. I keep confusing my dyslexia. Anyway, once you get the information out of it, you get all of this information. So it's all the settings that the BIOS has. Now, the easiest place to start is you just search for DCI. And let me get the font bigger. So the first thing I do is I search for DCI, and I find the setting DCI enabled, HDCIEN, that's the name of the register. And the offset is 538. I write it down, set it aside. DCI auto detect, current, I don't know if it's disabled or enabled, but disabled is 0, enabled is 1. Always double check. You never know when someone decides that enabled is 0. It's up to you, I guess. And then the offset, keep searching. XDCI support is also important. 56D, you remember these 3 offsets? And you're not done yet. This is just the DCI. Now, you need to enable debug. So
DCI is for PCH, CPU debug, or debug interface.
Debug interface
is for probe mode.
Debug interface.
If you want to access your cores and dump memory, things like that.
This is what basically sets the debug bit in IA32 debug MSR or C80. So this tells the BIOS to do it if the vendor hasn't disabled it. So what you do is you remember these offsets, 188, 189. The lock is the lock bit. The debug interface is the debug enable bit. You just set that one as on. I recommend disable the lock just to be safe. You never know whatever code in BIOS runs later. And that's it. So once you have these offsets, you go to your target machine. You boot it off UEFI. You go to this RU tool. It allows you to edit the non-volatile variables. You look for the setup variable, you jump to these offsets, and you make sure the bits are flipped. You save it.
Flash it.
It flashes it for you. You close the, shut down the machine, reboot it, and it's in DCI. See if I can. We have some time, right?
No, you
No.
actually
Okay, never mind.
over it.
Over.
So if anyone wants to ask questions, we can do it now. If anyone wants to hands-on, look at the cable, play with the computer, look at how it works, come find me. All right.
We have time for questions that we have. So if you have any questions, please line up at the microphones. No questions.
I'll give him time to think of a question. It's pretty straightforward. Yeah, go ahead.
Yeah, just go to the microphones.
Can you talk about those USB cables? What exactly happens under the hood, so to speak?
So, in a nutshell, the entire the JTAG is implemented in the 6th gen and above chipsets, right? So the USB cable is nothing but the medium. Whatever happens, whatever it's implemented, it's Intel's proprietary technology. If you want to look into it more, there's Peter Bosch and all the embedding and research that was published years ago, and BSSB and all that kind of stuff. That's quite a discussion.
So basically, the USB port on the device has also connection to JTAG on the processor, and that's as simple.
It depends. Yeah, yes and no. It depends. Some platforms don't have the traces connected to the CPU from the chipset. But in essence, yes. So the chipset handles the JTAG and goes
Gen
directly
6
to
and
the CPU.
above, it should. So you can just use the straight through cable and it should just work. Otherwise, you need the CCA that implements it for you. So
Yeah.
So your platform can talk DCI.
Yeah, if both platforms are 6th gen and above, you don't need CCA.
But this may be a confused question, but still. So any of the same tooling, could it be used for debugging and, just working with alternative, firmware implementations like, I don't know, core boot and stuff like that?
Yes. It's Intel architecture, right? All you need to do is flip bits and registers and MSRs. If you do that in core boot, you can do it.
To your knowledge, anybody is looking into that?
I remember last year there was an attempt to do something with core boot with that, but and when we did the OSFC in Germany, but I haven't seen anything.
Do you know Intel, Brian?
No.
Okay.
If anyone here in core boot, no.
Right.
Not every platform has DCI.
Understood, yeah.
Yeah, no, like some platforms, the manufacturers can fuse it off. So not every device would have it. There are known, if you Google, there are known models of machines. They're like, there's a couple of Dell Latitudes, there's a T460, there's Gigabyte bricks, so Gigabyte, MSI, again, all the good stuff.
Good stuff.
Why are you shaking your head?
For debug enabling.
For debug enablement. And ASRock also good for buffer overflows and remote code execution.
Where does one get a CCA?
So you go to designtools.intel.com and you start the process of an NDA, and then you pay them monies, and then you get a box.
The link is over there.
Yeah.
Although Mickey
Anybody
has
can
other
do
ways.
it, or
Yeah.
anybody could do it?
Anybody can do it.
Yeah, anybody can do it, as far as I know. But if you just don't want to have the hassle of the CCA box, just get a machine that's Skylake and above.
Right. Cool. Thanks.
We have time for 3 more questions.
3 more questions.
Very specific.
Wow.
Yeah, and 1 question
Or-
per person, please.
Or one really long.
Or 1 really long question.
One question is like we used to have is platform.
I'm sorry, can you please step a little bit closer to the microphone?
Yeah.
You can even like bend it down a little bit. So.
Okay.
Oh, there you go.
So this looks like a security risk. If you can debug a product.
I was waiting for this question. So it really depends on your threat model, right? If you consider physical access in your threat model, then yes. And that's what the settings are for. An OEM can choose to disable them, lock it, and remove the settings altogether to prevent users from using it. Then again, if your system is a server and you consider a data center or a protected place, it depends, right?
Okay.
In a perfect world, you won't be able to do debug in production. But we all know we don't live in a perfect world. So we can get to have fun in production systems. Yeah, one more
Yeah.
question.
You're right. If you wait long enough, people come up with questions.
Well, they got to think about it. Give them a chance.
Well, this is just a little more food for thought, more than a question. But we saw some of us were at the USB Anywhere reveal today, which basically meant Supermicro boards. It was a bug. Basically, through the BMC, you could attach a USB. So I just thought, wow, that'd be interesting to attach the USB and then get a hold of the DCI and
That's an interesting thought.
Really
Yes, you
interesting
think I just-
question.
I don't think it will work. I don't know about the implementation of it. I know it uses the medium over the USB stack, but it's not actually using the USB wrapping.
Yeah.
So I don't remember exactly if it's if the BSSB go inside the USB or if it's just BSSB without USB. So it just switches off to a DCI mode on the port, and then in that case, then you would have to emulate those packets, and not the same.
the USB is just the medium, and then it's using a different.
The USB is the physical medium.
Mhm.
I don't know what goes over the wire.
Right.
It may not be what compliant?
3.0.
Oh, it may not be USB 3 compliant.
But can you talk a little bit more then about the protocol that it talks? If it's not, it's not USB, it's something.
As far as I know, it's proprietary. There are efforts going on to reverse engineer it online. I don't know
what
anything
is the
about it.
protocol called, or does it have any?
I think that the
DCI?
DCI ITP,
Oh, DC. Okay,
just-
okay, cool. Thanks.
basically. There's a lot of acronyms and names when you talk about Intel products. All right.
Okay, then. That's about it for questions. Have another round of applause for Maggie and Mickey.
Thank you very much.
Thank you.
Thank you.